Hello everybody, we're going to talk today about the graphical explanation of displacement during constant acceleration. So we're just going to start out with, we're going to have our acceleration at a positive 10 meters per second squared. Our initial velocity is going to be 0. And the reason why we're going to do that is it's a little bit easier to understand when we start with 0. We'll say our time is 5 seconds, and our displacement is what we're looking for. Okay, so if we just do a little bit of math, we can see that since our acceleration is 10 meters per second squared, our time is 5, our final velocity is then going to be 50 meters per second. We've covered how to do that in another video. You just take your acceleration times your time. Okay, so if you would look at our formulas so far that we have, and we're going to use formulas and graphs to explain this. Well, we've talked about our average velocity being displacement per time, and we talked about our displacement being then our average velocity times time. The question is, kind of, what is our average velocity? So we did talk about our acceleration is v minus v sub naught, or the change in velocity per time. And if we have a 0 initial, then we can see that our velocity during acceleration, and velocity is final velocity, is equal to acceleration times time. Now, as long as this is a constant acceleration, we can then say our average velocity is v plus v sub naught divided by 2. Since v sub naught is 0, our average velocity then becomes v divided by 2. Okay, so if we look at these two equations and we substitute this in for v, we can say then that our average v is at divided by 2, and that would be, as long as we start at 0, we can talk about it this way. Even though we don't start at 0 in every situation, the average v that is caused from the acceleration will always have this relationship with acceleration. Okay, so if we go back to where we were on this other side of the paper, we can take this then and plug that in over here, and we can see that our displacement on this then is our displacement is 1/2 at, okay? That's our v, right? And then we have to multiply that by t, okay? So our displacement during acceleration, if velocity initial is 0, becomes 1/2 at squared. And that's the heart of one of our first kinematic equations that we get to use for the AP physics test. Now let's look and see how this all works out with the graph, because this is supposed to be a graphical explanation. So if we look at our graph here then, we can see that, I'll just draw a little graph here, and we'll say that we know that our final velocity here is 50 meters per second, and we know that we did this for 5 seconds. Okay, and since we start here at a 0 mark, we can see that the graph line is going to look like this, correct? Okay, so I did tell you before that, any graph has an area under the curve, and that means something. And how you figure that out is you just take your area formula, and everyone knows our area formula is base times height, right? If it's a triangle, a right angle triangle, we have 1/2 the base times height, right? In this case, this would be what we're using, correct? So if you look at this, you can see that this is a velocity, but since we're talking acceleration, we want to define our final velocity. And if you look at the little math that we did here a little bit earlier, you can see that our final velocity here is defined as acceleration times time, okay? So up here we could say that our final velocity is equal to acceleration times time. Okay, and if you look at our final velocity, we know that's not our average velocity, and when you go back to our mathematical description, we know that our average velocity right here is really what we're going for to figure out displacement, right? Well, we did find out that our average velocity is 1/2 AT, which makes sense, right? Because if we're constantly accelerating and we end at 50 and we started at 0, well then 1/2 of acceleration times time is going to be 25 meters per second, and that would be our average velocity in this case. Okay? So we can see then that our displacement of this graph is equal to average velocity times time. And keeping this in acceleration terms, our average velocity is 1/2 times acceleration times time times time. And if we look at the area under the curve, we can see that our average velocity here, which would describe this graph, would be, so instead of A, we're going to put X now, would be 1/2 AT, right? Because AT got us 50, and 1/2 of that is going to be our average velocity times time, because, you know, our height here is the 1/2 AT, and then our base here is the time. And we can see that X, following our area under the curve formula, is 1/2 AT squared. Okay, so you might be having questions about, well, what happens if I do have an initial velocity? Well, if I have an initial velocity, then what I have to do is we're just going to look at the initial velocity alone. Let's say I have an initial velocity of 5 meters per second. And we have to go with that same time of 5 seconds, okay? So we need to figure out what the area under the curve here is going to mean. So we have another velocity graph, and we have, 5 meters per second here. Let me use a different color. 5 meters per second here, and we do that for 5 seconds, okay? So if we look at the base times the height of this, area, base times height, in this case, the area is going to be meters per second times seconds, or the area is going to be equal to meters, which is a displacement. In this case, the area or the displacement is equal to 5 times 5. For the area under the curve, the displacement is 25 meters. Okay, so if we look at these two graphs together, okay, so we first off had our acceleration portion of the graph, and we came up with an area of an average velocity of 25 times 5. That was 125 meters. Was our average velocity, or our average velocity times our time, which gives us our displacement. Now this is kind of where it's a bit counterintuitive, or hard to think about, because this area under this graph alone is going to give us a displacement. Now if there's just acceleration and no initial velocity, we're going to have this displacement. But when we do have an initial velocity, then we have to add this displacement as well. So it's nearly impossible, well, it's probably not impossible, but I can't show you a way to put these two together on the same graph unless we superimpose them and we figure out their areas independently. But if you're going to try to find the overall displacement by using the area under the curve, we would have to go with two separate graphs. One is just the initial velocity times the time. And notice this time is the same as this time. And then we have to add that area to the displacement that occurs according to the acceleration. Now, if we would have a negative displacement or a negative velocity, we would be subtracting the two numbers instead of instead of adding them, but then you would find that these areas are in the negative y quadrant, the negative y positive x quadrant, and then it should be easy to tell that you need to subtract them. So let's see how this works here. Let's just make sure that our little formula works. So if we're trying to find displacement, then we should have, according to our graphs, v sub naught t, which will be one area, plus 1/2 at squared, which will be another area of another graph. But keep in mind here that, don't let your math skills go away from you. In reality, if this is a meter, then this has to be a meter, and this has to be a meter too. So every one of these individually are a displacement, or they look different, but they're all meters. So let's just try to plug in our numbers now that we graphed. Let's say our acceleration is 10 meters per second squared. Our time is 5 seconds. Our initial velocity is 5 meters per second. And we're trying to find out our displacement. So if we take our two graphs and add them together, we can see that our displacement should equal v sub naught t, initial velocity times time, plus 1/2 the acceleration times time, which is an average velocity. This part right here is an average velocity caused by the acceleration times time. So velocity times time is another displacement. And keeping in mind, these t's are definitely the same t, the same number. We'll just fill in our numbers here. Our initial velocity we said was 5 times 5. Our acceleration is 10 and times 25. So we can see that we have 25 plus 125. Our final displacement should be 150 meters. Now, if that formula and our graphing is correct, we should see the same answer with that. And sure enough, we do see the same answer. We have a displacement of 125 due to our acceleration, and we have a displacement of 25 due to our initial velocity. Hopefully that clears up some of the questions you had in class today. Have a good day. Thanks.